Okay, so now let's imagine that we have multiple charged particles and that we do some experiments and we recognize that the field, the electric field at any one point, is just a sum of the fields produced by the different charged particles. So let's create our XY axis, and let's do an example where we have two charged particles. Let's say that at x equals a and y equals b, so this is y equals b, we have a charged particle q star. Okay, so a particle of charge q star is sitting there, and at a equals minus b, at x equals minus a, and at y equals b, we have a particle of the same charge, q star. So I didn't draw that very well, but let's make it a little bit bigger. So they're at the same height, if you will. And if we draw their electric fields, so let's make one electric field in red. The electric field diverges radially away from the charged particle. So here are a few field lines. And at this location, the field to this one would be something like that. Here it's something like that, and so on. And let's make the field of the other particle blue. So we want to be symmetric, so the field line here goes like that, and the field line at this location goes like that. Let's make a few more field lines like this. The arrows are getting smaller as we're moving away. Of course, these field lines, there are blue field lines over here as well, so there's a small blue line there, say, and there's a small red field here. And so we could continue, mapping out the electric field everywhere in space. But what's clear is that at this location, the electric field, the net electric field that's produced in space must be zero, because you have a red electric field pointing left and a blue electric field pointing right, and they have the same magnitude because both charges have the same value and they are at the same distance from this point. So let's find the net electric field in the xy plane, and then let's evaluate it at this location. Right? This is x equals 0, y equals b. So let's evaluate the field there, and let's make sure that in fact it goes to 0. So the electric field is just the sum of the two electric fields. So it's the electric field of the particle over here. Let's write that electric field first. It's k q star times x minus the x value of the particle that creates the red field, which is x equals a. So we have x minus a, I hat, plus we have y minus b, j hat. And we want to divide that by something through the 3 halves. That something involves x minus a squared plus y minus b squared. So that looks like that. So let's just call this the electric field 1, where the particle number 1 is over here and particle number 2 is over here. So particle number 1 produces that electric field, and particle number 2 produces an electric field that depends on the coordinates of particle number 2, and that's kq star, because it has the same electric field. Sorry, it has the same charge. Now we have x minus the x coordinate of this particle, but that's minus a. So we get x minus minus a, that's x plus a, I hat, plus y minus b, that's unchanged, right? That's the same as for the other particle. And we divide that by x plus a squared plus y minus b squared, all of this to the 3/2. Okay, so the net electric field is just the sum of these. So the electric field, let's say total, at every point in space, is just the electric field 1 added to the electric field of particle 2. Okay, so let's see what E total is at x equals 0, y equals b. And we expect it to be 0. Let's see if that is indeed the case. So E1 looks like what? So we have k q star times open square brackets. We have x equals 0, so here we get minus a I hat, plus we have y is equal to b, so we have b minus b is 0, and the other term goes away. So we only have a term like that. And in the denominator we have 0 minus a squared, so we have, that's the same thing as a squared, plus b minus b is 0, so we have a squared to the 3/2. And now we're going to add to that electric field 2 evaluated at x equals 0, y equals b. So what does that look like? Well, we have k q star times x is equal to 0, so we have a I hat, and y is equal to b, so this term again disappears, and we divide that by, sorry about that, we divide that by 0 plus a squared, but that's the same thing as a squared, just as we have over here in the denominator, plus b minus b is 0, so that term goes away. We have the exact same thing in the denominator, and so we can add the numerators, and then we see that we have minus k q star a I hat plus k q star a I hat over, we can simplify that to a cubed. And in fact, the electric field there goes to 0 as expected.